In this video, I want to talk about the Lorentz transformation in special relativity. I'll talk about some paradoxes, like the tunnel paradox and the ladder in a barn paradox, and at the end I'll show a visualization of the Lorentz transformation when there's more than one spatial dimension, as well as the aberration of light. All of the Desmos files I'll show today will be linked in the description of this video, and I encourage you to go play with it yourself. Interacting with visualizations like this is one of the best ways to get an intuitive understanding of the situation. So let's begin with the spacetime diagram. This is a two-dimensional diagram. This is the x-axis, and this is the time axis. This is showing the situation of an object traveling through one-dimensional space over time. Remember that even though this is a two-dimensional diagram, there's only one dimension of space that the object can travel in. As time increases, this blue object is moving to the right, and I can adjust how quickly that object is moving by dragging this slider over here. This number is the blue object's speed as a fraction of the speed of light. And you can see that these 45-degree lines represent the speed of light, the maximum speed allowed under special relativity. Now I've added a second orange object over here, which is traveling to the left at 3/10 the speed of light. And the point of the Lorentz transformation is to see the universe under a different perspective. When you are in some object's perspective, that means you must be stationary relative to them. If you want to see the situation from the blue object's perspective, the blue object must be stationary, and it must be traveling vertically upwards in the spacetime diagram. So by adjusting this slider B over here, I can transform the entire situation into the blue object's perspective. And what you see now is that everything else is shifted. The orange object used to have 3/10 the speed of light to the left, and now its velocity is much closer to the speed of light. You'll also notice that these grid lines are still all lines, and that's because the Lorentz transformation is a linear transformation. You could, if you want, write the transformation in terms of matrices. And so the visualization I have over here is essentially identical to the visualization that 3 Blue 1 Brown gives in his Essence of Linear Algebra series. One of the most important things about special relativity is what's called the spacetime invariant. It's a quantity that remains unchanged as you apply the linear transformation. If you observe an event in space and time, every individual will agree on this spacetime invariant for that event. In this diagram, the y-axis represents time, and the x-axis represents x, and the spacetime invariant is time squared minus x squared, or in this case, y squared minus x squared. If you set that equal to a constant and visualize it on the diagram, you get a hyperbola. And let's adjust this constant so that the hyperbola touches the tip of the orange line, maybe about 0.95. The tip of the orange line over here is an event in space-time. Maybe this is a spaceship traveling to the left, and at this location and at this time, a light bulb turns on in that spaceship, or a small explosion happens. This event is agreed upon by everyone, and as I apply the Lorentz transformation, that event stays on this space-time invariant. This red line is a collection of all space-time events with the same space-time invariant. Different people traveling at different velocities will see this event here happen at a different position and a different time. But the one thing they can agree upon is this value C0 over here. Everyone agrees that this orange event happens somewhere on this red line. So now let's enable a whole collection of these spacetime invariants, these hyperbolas. Again, under the Lorentz transformation, every event in spacetime follows one of these hyperbolas. And that corresponds to the fact that this quantity, this y squared minus x squared, this time squared minus position squared, is always a constant for each event. There's an analogy that can be made here. You can think of the Lorentz transformation as a function that takes in a two-dimensional input, which is position and time, and gives a two-dimensional output, which is the transformed position and time. This is a transformation from a 2D point to a 2D point, and another common transformation like this is a rotation in 2D space. This is no longer necessarily a space-time diagram. You can just think of it as two dimensions in space. But now the coefficients of this transformation are such that as I drag this value b, the entire coordinate grid rotates instead of stretching like a Lorentz transformation. And now the invariant is no longer these hyperbolas in the Lorentz transformation case, but rather the invariant is this, y squared plus x squared. As you rotate any given point, the value of its y-coordinate squared plus the value of its x-coordinate squared remains constant regardless of how much you rotate. And this is algebraically expressed as y squared plus x squared equals a constant. Another way to say that is the quantity y squared plus x squared is invariant under a rotational transformation. So now let's look at some common paradoxes within special relativity. One of them is the tunnel paradox, and it stems from the idea of length contraction in relativity. From the ground's perspective, because the train it's moving, its length should appear contracted, and so it can fit inside a tunnel. But from the train's perspective, it's the tunnel that's moving, so the tunnel's length should seem contracted, and the train shouldn't be able to fit inside the tunnel. We can create this situation in Desmos on a spacetime diagram. In this diagram, the red lines represent the tunnel, the blue lines are the front and the back of the train, and when the red lines are dashed, that means the door at that side of the tunnel is open. So remember, in these spacetime diagrams, there's only one spatial dimension, and the correct way to imagine any situation in your head is to imagine a horizontal slice of the spacetime diagram like this, and see how the objects move as this line moves vertically upwards as time progresses. So initially, at negative time, the train is coming in from the left, and both doors are closed. As the train begins to enter, the left door of the tunnel opens, the back of the train now enters, and at this moment in time, the train is able to fully fit inside the tunnel because its length is contracted. And then later, the front of the train reaches the back of the tunnel, that door opens, and eventually the back of the train exits. But now let's look at the entire situation from the train's perspective. We can do this by applying the Lorentz transformation until the blue lines, the lines that represent the train, appear vertical. And that indicates you are not moving relative to the train. From this perspective, the orange dotted line is what the line of simultaneity looks like. The train remains stationary, and the tunnel apparently approaches from the right. The door opens, the train enters, the back door opens, and the front of the train exits the back of the tunnel, before the back of the train enters the front of the tunnel. From the train's perspective, the tunnel is much narrower, and there's no moment in time when the train is entirely within the tunnel. This apparent paradox from length contraction is fundamentally accounted for by the difference in simultaneity. If I enable the green line of simultaneity again, this line is what is apparently simultaneous from the tunnel's perspective. And you can see that what was simultaneous from the tunnel's perspective is no longer simultaneous in the train's perspective. That's why it's possible why there's no moment in time when the train is entirely within the tunnel from the train's perspective, but there is a moment in time when the train is fully inside the tunnel from the tunnel's perspective. Now let's move on to another apparent paradox. A runner is carrying a pole and is running at near the speed of light into a barn. Let's say that the barn has a solid wall at the back and a door that can open and close very quickly at the front. Let's say that when the pole is stationary, its rest length is longer than the length of the barn, so that it would be impossible for the pole to fit inside the barn with the door closed. But if the runner runs close to the speed of light, the pole should experience length contraction, and from a stationary observer's perspective, the pole would be able to fit inside the barn, and the door would be able to close. However, from the runner's perspective, it's the barn that's moving, and so the length of the barn will appear even shorter, and there won't be a moment in time when the back of the pole enters the barn and the door closes. So here's the paradox. Everyone has to agree whether or not there's a moment in time the pole is contained fully within the barn. The door closing is an event that happens at a specific point in time at a specific point in space. There's no way that anyone can disagree on whether the pole is contained within the barn or not. So how can this paradox be resolved? Let's look at the spacetime diagram of this situation. The red lines are the walls of the barn, the blue line is the front of the pole, and the green line is the back of the pole. This slider here controls the velocity of the pole, and when the pole is at rest, its length is longer than the length of the barn. So let's see what happens when the pole is traveling initially at 80% the speed of light. The pole comes in from the left, and the blue line intersects the red at time equals 0. At this time equals 0, the back of the pole has already entered the barn. And now here's the crucial point. No information can possibly travel quicker than the speed of light. So the back of the pole wouldn't know that the front of the pole has impacted until that information can be sent to the back of the pole at the speed of light. So between this time and this time, the back of the pole will travel at its original velocity. So not only will the pole fit inside the barn at t equals 0, but as time progresses, the pole gets compressed more and more. There's no such thing as a perfectly incompressible material under special relativity. Now you can ask, what happens when the signal does finally catch up to the back of the pole? Well, now the atoms inside the pole suddenly find themselves compressed much closer than their natural distance. So interatomic forces will start repelling the atoms away from each other, and the pole will then expand, and eventually the back of the pole will punch into the door of the barn, and either break that door, or if the door is strong enough, the pole will remain inside under extreme compression. We can see that this situation also makes perfect sense from the pole's perspective. If we apply the Lorentz transformation and make the pole appear vertical in the spacetime diagram, we see that it's the barn that's apparently moving from right to left. The front of the pole enters the door of the barn, and at time equals 0 impacts the back of the barn. Now the front of the pole and the back of the barn keeps traveling at near light speed velocity to the left. But as time increases, the back of the pole wouldn't know that the front of the pole has been impacted until this light speed signal indicated by this black dashed line reaches the back of the pole. And you can see that by the time that happens, the back of the pole has already entered the front of the barn. And now not only does the entire pole travel to the left with the barn, but the pole also expands because it's been contracted to below its natural length. And eventually the pole will either break the door or get stuck there. We've seen enough of the 2D spacetime diagram, so now let's have a look at a 3-dimensional diagram. In this diagram, the vertical axis is time, and the x and y axes are space. So this diagram shows 2 dimensions of space and 1 dimension of time. We can again think of objects traveling inside this space, which is indicated by these lines. Now let's consider motion along the x-axis, and see what happens when we apply the Lorentz transformation along the x-axis. You can see that the grid only stretches and squeezes along the x-axis and time axis, but not the y-axis. If we look from this perspective, as the grid stretches and squeezes, nothing along y changes. If we look perfectly from the side, this grid now moves in exactly the same way as the 2-dimensional situation. The spacetime invariant still holds in this 3D diagram. In this case, it's negative time squared plus x position squared plus y position squared equaling a constant. If I plot that on the 3D graph, what you get is a hyperboloid. And that makes sense. In 2D you get a hyperbola, in 3D you get a hyperboloid. You can see that this orange point is on the surface of the hyperboloid right now. That means as I apply the Lorentz transformation, the orange point will stay on the surface of the hyperboloid. Now let's enable the light cone, and this is the cone of rays that travel at the speed of light from the origin. You can see that if I turn off this hyperboloid, the orange point is inside the light cone, and this purple point is outside the light cone. There's a name for these properties. The line from the origin to the orange point is what's called a time-like interval, and the line from the origin to the purple point is what's called a space-like interval. As you apply the Lorentz transformation, if you begin as a space-like interval, no matter how much you transform, you will always stay as a space-like interval. You will never be able to cross the light cone. And the same goes for time-like intervals. If you start off inside the light cone, the Lorentz transformation will never allow you to cross the light cone. What we can now see is what happens when you vary the space-time invariant. If I now hide the light cone and change this parameter over here, you can see the hyperboloid slowly changing shape, and now becoming a hyperboloid of 1 sheet instead of 2 sheets. And now the hyperboloid intersects this purple point, and as I apply the Lorentz transformation, the purple space-like interval stays on this hyperboloid. The final thing I have to show today is the aberration of light. Let's suppose you have this green object over here which is radiating light over time. It's radiating light, so from its perspective, the light rays go out on the xy plane at equal angle spacings. Now let's consider an observer which is moving relative to this object that's radiating light. If we apply this Lorentz transformation to make the purple line vertical, the object is now apparently moving towards this observer. And if you look at the situation from the top, the light rays in the object's direction of motion apparently get compressed together, and the light rays moving opposite apparently get stretched out. And notice that these light rays still stay on the light cone under the Lorentz transformation. This is not something I've explicitly told the orange lines to do in this Desmos file. I'm simply applying the Lorentz transformation to these orange lines, and since they started off on the light cone, the Lorentz transformation automatically guarantees that they stay on the light cone. So that's how the direction of light changes. Now let's see how the frequency of light changes. One way to think about the frequency of light is to think about the peaks and troughs that the object releases. If I look at this object from the side and drag this T cutoff slider, it's cutting off the light rays. And we can imagine the object emitting peaks and troughs of light at regular intervals in time. So the final result is, if you look from the top, in XY space, from the object's perspective, the wavefronts travel out in circles. But now, what happens if we apply the Lorentz transformation? As the transformation happens, you can see that the peaks and troughs shift to the side. And you can see that at the end, if we look from the top, the side of the wave that is traveling with the object gets compressed, the wavelength shortens, the energy increases, and the side of the wave traveling opposite to the object gets stretched. The wavelength increases and the energy decreases. You can equivalently think about this in terms of frequency as well. If you look at the situation from the side and imagine vertical cross-sections, the vertical distance between peaks and troughs gives you the frequency of the light. And over here, the frequency is higher and the energy is higher. Over here, the frequency is lower and the energy is lower. You'll notice that these cones stayed as 45-degree cones. Again, that's not something I've told the Desmos file to explicitly maintain. I've simply plotted these 45-degree cones and applied the Lorentz transformation to them. And the Lorentz transformation automatically guarantees that these 45-degree light cones stay as 45-degree cones. So that's all I have for this video. I hope that seeing me drag around these sliders has increased your intuition for these ideas of special relativity. And again, all of these files are linked in the video's description, and I highly recommend you go play with them yourself. Interacting with these situations is one of the best ways to actually understand them intuitively. That's all for this video. See you next time.